Let's talk about convection heat transfer. Convection heat transfer is transfer due to the So is a heat transfer due to the molecular or bulk motion of the medium, which is liquid and gas. Suppose that we have a solid surface, so all surface, and there is a fluid that is moving on top of this solid surface. From fluid dynamics, you would remember that if this fluid is flowing, what we are going to see, so what we are going to see here is when flow is flowing through this flat surface, we will have no slip condition at the wall. So here the velocity will be 0. And as we move away from this wall, the velocity will keep increasing till it reaches to the free stream velocity, which is u infinity. And after that, the velocity does not change. Now this forms a hydrodynamic boundary layer. And then we get the velocity distribution. Which is u of y. And I'm just showing it with this one. Now, similarly, when the temperature of this flat surface is different than the fluid, so let's say our fluid is with the u infinity and then it has a temperature of T infinity, and let's assume our solid is at TW, T of wall, which is different than the fluid. And let's assume this temperature is less than the temperature of the fluid. Then what we are going to see here, we are going to see decrease from the wall till we reach to that one. So if I just show the magnitude of this temperature, this is going to be T wall. And then we are going to have the decrease in the temperature till we reach to the temperature of fluid, which is T infinity. And then at some certain point, it doesn't move. And similarly, what we have here is we have thermal boundary layer, and we have this temperature distribution. That starts from TW all the way to T infinity. Now, since TW is greater than T infinity, we expect to have transfer of heat from the solid surface to this moving stream or to this flow stream that happens here. Now, how we show that, or the amount of heat, the rate of heat transfer is defined by Newton's law of cooling, which state Q, heat transfer, is equal to HA TW minus T infinity. And TW, we have TW, we have T infinity, we have A, we have H. TW is the wall temperature. T infinity is free stream fluid temperature, and A is exposed or wetted surface area. If I look at this wall, it could have extension of here, and that's the area that is exposed to this heat transfer. And H here is heat transfer coefficient. Temperature, unit of Kelvin, and heat transfer coefficient has a unit of watt per meter square Kelvin. H, heat transfer coefficient, depends on average velocity that is passing through, or Reynolds number. We will see that later on about like this heat transfer coefficient. Now, in terms of convection, of course, this flow can just pass by forced convection through some mechanical forces, or it could be natural, or there could be different things that can happen. So we can have different modes of convection, which is natural convection, and natural convection, the fluid motion is solely due to buoyancy. And so you would see that, like, let's say if we have a vertical plane, the less dense fluid, it starts to rising up. Now, of course, the angle this plane is making with respect to the vertical side, like if it's like that, or it's going to make a difference in terms of like the heat transfer coefficients that we are going to see here. Now, the other one is forced convection. Where the fluid motion is due to mechanical forces. We can have a fan, we can have a compressor, we can have a pump that's forcing the fluid to move. The other one is condensation or boiling, where we see change of phase from liquid to vapor or from vapor to liquid. Now, if I want to bring some example of that, of each of them, let's say you have a coffee mug and that's exposed to air. So coffee mug surface to air. What mode of convection that we have? In terms of convection mode, we are dealing with the free convection. And in terms of heat transfer coefficient with the unit of watt meter square K, it's going to be around 10 in the side that is exposed to the air. Air is just flowing at the top, and it's going to be around 200 for the liquid or coffee here. The other example, when air flows at 45 meters per second at your face, what we have here is forced convection, and the heat transfer coefficient is around 100 in the air side and is around 1000 on the liquid side. The other example, let's say when we have a condensation in a horizontal tube, what we are dealing with the boiling condensation mode. Condensation mode, and the heat transfer is huge, is around 10,000 watt per meter square Kelvin.